Hi everybody, happy Wednesday. Your exams are on the back of the table if you haven't picked up the graded work. Today we're going to be talking about section 2.5, the chain rule. Friday we're going to be discussing implicit differentiation. And Friday's quiz 3. I just posted quiz info for quiz 3 on the webpage. A few comments on the exam. Which of these equations is true? One of those we actually haven't encountered yet. So 1, 2, 3, 4, 5 equations. Any comments on which of these are true, which of these are false?
The first two are false.
Okay. Why?
Those are the derivative rules for sine and cosine. They don't equal each other.
Yeah, sine and cosine are not the same function. They're just simply not the same function. There are some x values where sine of x does equal cosine of x. Pi over 4 is an example, 5 pi over 4 is an example. But these are not the same function. So the correct relationship is d dx of sine x equals cos x. So you want to always write equations on your page that are correct. It doesn't take much time to write the right thing. How about this one? Ln of x equals 1 over x. Yeah.
Is he correct?
Who knows what Ln of x looks like? Raise your hand if you know what the graph of Ln of x looks like. Now raise your hand if you know what the graph of sine x or cosine x looks like. Yes, a lot of you have, if I locked you in a room and said, figure out if this equation is true, you could make the graphs and you could figure out, oh, again, this equation is not true, those graphs are true. But nobody seems to remember what Ln of x looks like. That's just the plight of Math 2301 students. So most of you are not equipped to know whether this is true or not. But trust me, if you write this 20 times, you're going to start to think it's true. Trust me. I've seen this written thousands of times over the last 30 years I've been teaching. Thousands of times I've seen students write this. And it gets to where they think this is true. And so students will, when they see Ln of x, they'll just replace it with 1 over x. The thing is, this is not true. The relationship we're going to find out next week is that the derivative of Ln of x is 1 over x. Again, you might not be equipped to assess this because you're rusty and you don't remember what the graph of Ln of x looks like. But this is not true. This is the relationship. So it's important that you write down stuff that's true. You might think, I'm just going to save time, I'm just going to write this. Well, no. You write that enough times, and you're going to start to think that it's true. So, and also, you want to present stuff to the reader. You want to present equations that are true. You should be writing down sentences that are true. You shouldn't be having something like this. This is not true. This is a bad writing of the code. The correct relationship is the derivative of x to the n equals n x to the n minus 1. Now what about this one? Well, let's see. Let's ask this question. When is sine x? Now, think about this equation. This equation is not true. Sine x and cosine are not the same thing. But there are some x values where sine x does equal cosine x, as I said. And it's just like the old saying, a stopped clock is true, is right twice a day. Your watch stops at 11:37, well, twice a day, your watch is going to have the right time. So let's ask this. When is sine of x equal to sine to x? When is that true? Well, let's make a graph of sine of x. And let's make a graph of y equals x. Anybody see an x value where those y values are the same? Yeah.
0, 0.
Yeah, put them on the same graph. Here's the graph of y equals x. Here's the graph of y equals sine of x. In fact, the graph of y, the line of y equals x is the line that's tangent to the graph of sine of x at the point 0, 0. And you can see that in this case, that's the only place those graphs touch. That's the tangent line, it's also the only place where they touch. So sine x equals x is only true when x equals 0. So now how about this question? When is sine x over x equals 1? When is that true? Well, I'm saying at what x value there? It's never true. Because if this is true, I multiply both sides by x and I get this. So if this is going to be true, then this is going to have to also be true. Well, the only place where this is true is when x is 0. But then when x is 0, this is undefined. So the thing is, this equation, it's just simply never, ever true. So a lot of exam papers, students on problem number 3 about the limit, a lot of students gave some argument. They said at some point, because this. Well, that's not true. If you have an argument that's based on this fact, your argument's just no good. Doesn't matter if you have a numerical answer that comes out right. If you got there by using this fact, your method's just no good. You're just misunderstanding the limit. So on the so as who was it over here? Somebody said, what is true is the limit as x approaches 0 of sine x over x is equal to 1. That is true. Now, remember I've said before that I don't cover all the problems that you're going to need to know in the course. And especially if something is done well in the book, it's not a good use of my time to cover it in class. I want to cover stuff in class that's not covered in the book, or that I want to cover a different way. In lecture, I mentioned this problem. You had a homework problem that said, find the limit as x approaches 0 of sine 3x over x. And I said, there's this homework problem you've got to do. I'm not going to discuss this in class because there's an example like it in the book. There's the example. It's the problem from the exam. I didn't even change the numbers. It's the exact problem. Now, if you look at this, the trick is multiply and divide by 7. So there's the dividing by 7. Oops, sorry. So you multiply it and divide it by 7. It's a trick. So this expression is the same as this expression. But then when you park the limit in front of it, trying to make this large enough that you can read it. So when you park the limit in front of this, that's the same as parking the limit in front of the other one. The 7/4 comes through, and you're left with the limit of 7x over 7x, which can be turned into this limit. And there you can use that expression that the limit does equal 1. But a bunch of you just replaced sine x over x with the number 1, said that that's true, and that's just not the way the limit works. It just isn't the way the limit works. So I want you to be able to show why these answers turn out the way they are. So this is sort of my ongoing nag to read the book. And getting to the book, remember you go to WebAssign, you click on this WebAssign for Stewart Essentials. That brings you to this page, and you click here on ebook, and that brings you to the book. So you want to make sure that you're making use of the book. All right, that's my rant about the exam. Problem number 4 on the exam, that's the one about prove that there's a solution of cos x equals x. That's a homework problem that was also a recitation problem. All right, meeting part 2. Is the chain rule. Which is section 2.5. So I would first want to talk about what I would call, what are commonly called compositions of functions. I call them nested functions. So the symbol, so for functions f and g, this symbol is a symbol for a function. It's called f composed with g. And it's defined by, I have to tell you how it works if you feed feed it input? How do you get output? So I have to take that symbol, F, open circle G, that's the name of my function. So I'm going to put that whole name in parentheses because I want to make it clear that that's the name. And then I want to feed that thing an input. And the way this works is you take the input, and you first feed it into G, and then you feed that into F. So what I call nested functions I'm going to call these things nested functions. They're functions of this form: outer parentheses inner parentheses x. So that could also be denoted outer open circle inner. So the chain rule is used for taking the derivative of a nested function. And it says this: the derivative of one of those babies, so outer parentheses inner parentheses x, is this: outer prime parentheses inner of x times inner prime. So, for example, I'm going to try to get through some good examples. Find the derivative of f of x equals x cubed minus 12x plus 16 all raised to the 5th power. Now, as I always do, I start by writing down the things that we've been asked to find. We've been asked to find f prime. And I want to write down sort of generally what that means. It means we're going to be doing this: d dx of that baby, x cubed minus 12x plus 16 raised to the 5th power. Now, just as when I do those tangent line problems, I always say that I always do the same thing when I solve tangent line problems. I write down the expression that we need to build. When I do chain rule problems, I always do this. I write down the form. So in other words, I acknowledge that what we're looking at here is the derivative of outer parentheses inner parentheses x. Just to remind myself and the reader what we're looking at here. We're looking at the derivative of a nested function. And this, then, is the left side of the chain rule. So then I'm going to write down the right side of the chain rule. This is outer prime, parentheses inner, parentheses x, times inner prime of x. So there I've used the chain rule. Because on one line I have the left side of the chain rule, and the right side I have on the next line I have the right side of the chain rule. So over to the side, I always put this on the side, the dirty work, the chain rule, dirty work. So first first of all, what's up with this? I mean, I swapped out this symbol, then I introduced these new terms. I should properly introduce them. So what is my inner of x? Yeah,
X cubed minus 12x plus 16.
great. Now, skip a line here. I want to write down my outer function. Now, my key to solving chain rule problems is that the outer function I always write as an empty function. So I'm not going to write outer of x, I'm going to write outer of parentheses. So who can tell me what the outer function is as an empty function? Great. Parentheses to the fifth. So this is the empty version of the outer function. Now look, that's the introduction. So that gets us to this line. This line tells us what we're going to need. We're going to need inner prime. Okay, well that's why I said to leave a blank line here. Because what I want to do here is I want to put in what inner prime is. Inner prime of x is apparently something we're going to need right here. So what is inner prime of x? Somebody in the north side up there. If that's inner of x, what's inner prime of x?
3x squared minus 12.
Great. Now, if this is outer of parentheses, we're going to need outer prime, and it's going to need to be empty. What if that's outer of parentheses? What's outer prime?
5 parentheses to the fourth.
Wonderful. So the derivative of 5x, derivative of x to the fifth would be 5x to the fourth. The derivative of t to the fifth would be 5t to the fourth. The derivative of parentheses to the fifth is just 5 parentheses to the fourth. So I put all that stuff over on the side. And then I assemble my parts. So I have to go get my outer prime, which is 5 times parentheses to the fourth. And I have to stuff them with the original inner function. And then I have to multiply by my inner prime. All right, how did I do? Yeah, whenever I say how did I do, it's usually indication that I made some mistake, and half the time it's the wrong parentheses. So these are crucial. If you leave off those parentheses, you've written down the wrong thing. It doesn't matter if you had the right thing in your head. What's important is that you write down stuff in the right way. And there we go. That's the derivative. All right. Everybody scoot up next to somebody. Is the sign-in sheet making it around the room somewhere? Great. Did everybody sign in? Who didn't sign in, make sure you sign in. So scoot up next to somebody. This is great. We've got groups of 2, we've got one group of 3. Oh, actually, maybe, could you, oh, are you working together?
Yeah.
Okay. All right. So, oh, maybe you could come down and make a group of 1. You could make a group of 2. Thanks. Okay, so example 2. So for this function, we have for f of x equals cube root, square root of x cubed minus 12x plus 16. A, find f prime of x. Now I'm gonna be quiet now and let you work for 5 minutes, and I'm gonna write the rest of the problem while you're working. All right, a bunch of you are doing the right thing. A bunch of you are doing the right thing, but with some mistakes. So here we go. Let's give it a go. So f prime of x is the derivative of this thing. Now I'm going to go ahead and write this as a power function. And so I'm going to write the form. This is the derivative of outer of inner of x. And so the chain rule says that I need to do this. Outer prime of inner of x times inner prime. Now, remember, I always do, not just when I'm teaching that I do this. This is the way that I work. Chain rule dirty work. So part of this is easy. We have the same inner function. Inner of x is again x cubed minus 12x plus 16. So inner prime is again 3x squared minus 12. Now, what's my outer function though?
Square root of x, or square root.
Yeah, but remember I wrote it as power.
So parentheses to 1/2.
Yeah, parentheses to the 1/2. Now, what's my outer prime? Yeah, and let's do this in baby steps. 1/2 times parentheses to the 1/2 minus 1. So that's where you get 1/2 parentheses to the minus 1/2. But that's not simplified, right? You can't leave something in negative with a negative exponent. So how do I rewrite that? Huh?
1/2 parentheses, wait, at least 1/2 square root.
So just do baby steps. So just deal with the minus 1/2.
1/2 parentheses,
No, just that. 1/2 times
minus
1 over parentheses to 1/2. So again, baby steps, only one step at a time. Do not try to do more than one step. Now this can be written as 1/2 parentheses to 1/2. And if you want, that can be written as 1/2 square root of parentheses. But there are 1, 2, 3, 4, 5 steps to get here. A lot of students have, on the exam, I noticed a lot of students had trouble with the exponent stuff. Like they wrote 1/x as x to the minus 1/2 or something. This stuff is, it's easy when you see somebody else do it, but you want it to be bulletproof. You know, the power rule, write down the arithmetic that you're going to have to do. When I walked around the room, I noticed that some of the people have the wrong expression written down here, and it's because they didn't do this. Again, if you don't do this, you just do all this stuff in your head, there's a good chance you'll make a mistake. I mean, there are 5 baby steps here. 5 baby steps is no longer a baby step. It's something that's significant enough that it's quite possible to make mistakes. So you want to get to where you can articulate these individual steps so that it's reliable. And then you assemble all of those and you get 1/2 square root of, then I've got to have x cubed minus 12x plus 16 times 3x squared minus 12. How did I do? Need parentheses. How did I do? There's still something wrong. Over 1? Right, so the idea here is what does that symbol mean? 1/a sitting next to b. Does that mean 1 over the quantity AB? Or does it mean 1/a times b?
It's 1/AB.
One vote for 1/AB. Okay. Why?
Because the only thing that's in, like if we take the formula of outer prime inner times inner prime.
Oh, I'm just talking about
Oh,
general
okay.
and arithmetic here. Yeah.
It's because the division sign between 1 and the A doesn't really move into.
Yeah, but two things are being done to the A, right? It's in the denominator, there's also a multiplication symbol there. Which of those happens first? Doesn't multiplication happen before division? Okay, PEMDAS, parentheses, exponents, multiplication, division. So apparently multiplication happens before division, but not really. Thing is, this is bad news. It doesn't matter what you think it means. It doesn't matter what the rule is. Half the people in the world are going to read this one way, and half the people are going to read it the other way. So to write something like this and tell them to go build the bridge is suicide. You know, don't write this way. Don't write that. You're asking for trouble. Whatever you think you meant. The reader might not do this. So when I said, how was I doing? It's what, were you the one who was talking about? Yeah, so this, you know, to multiply a fraction by something that's not a fraction, you can do this, or you can put the thing up in the numerator, you know, but the thing is there's a baseline for this equation, and it's not the floor, it's this line. So if you want this thing to be on the baseline, it can look like that, or it can be like this. But it should not be on the floor. The floor is not the baseline. Because again, this issue, just handwriting, it's bad, it's a bad idea to write something like this. Wonderful, that's it. So I'm going to shut up again. Find the slope of the line. Oh, wait, before I forget. Notice it's the same problem, right? I mean, this is the exact same problem as this one. It's just that it's a power function problem. The power happened to be a little bit different, so I had some more steps to go through, but it's the exact same problem. That's another reason that I set these up this way. It's like those tangent line problems. If you always set them up the same way, you start to recognize the forms of the solutions, and you can be assured that you did the right thing because you're just doing the same thing you always do. I describe myself as a mathematical hedgehog. I don't know if you know the idea of the fox versus the hedgehog. The fox is the clever one that always figures out some unique way of solving every problem. The hedgehog just does the same damn thing every time. I'm a hedgehog, and I like to do the same thing every time because I get used to it. And you catch a lot of mistakes if you make sure that you stick to a form. All right, so that's question A. So I'm going to let you work for a few minutes on this. Find the slope of the line tangent to the graph at x equals 0, and then also find the x-coordinate slope. All right, let's resume. So question B. I want to start with this. What's going to go on the left side here? Should be a symbol for what we're being asked to find. Even more primitive than that, because we weren't asked for f prime 0. We asked for the slope. So a good symbol, I think, would be m. M, that's the reader would understand why I put that there, because we were being asked for m. And then you made the connection that what we want to compute is f prime parentheses 0, because that's the particular qualifier. Which slope? Well, the slope of this line. And so that means to go get this formula and plug in 0. So 3 times 0 squared minus 12 over 2 times the square root of 0 cubed minus 12 times 0 plus 16. So that's minus 12 over 2 square root of 16. So that's minus 12 over 2 times 4. So that's minus 3 over 2. Now, how do I start this calculation? Got one hand up, 2 hands. Yeah.
You find when the derivative is 0.
So what should I write first? Yeah.
F prime of x equals 0.
Yeah, and I would turn that around. I wouldn't even say f prime of x. I'd say 0 equals m. That's the key thing. In the first question, we're trying to find m. In this case, we know m. We know that m is 0. And that's f prime of x. So to the reader who's a little bit clueless, like what's going on here, they might say, why are you talking about f prime of x? Well, hit them on the head and say, we know the slope is 0, and then that's what f prime of x is. So, all right, now, I don't know if I have any more of my cool blue chalk. But remember, what has to be true for A over B will equal 0? Because this is a really ugly equation, right? 0 is this god-awful mess. Yeah.
B can't equal 0.
B cannot equal 0, and what else has to be true?
A doesn't equal B.
Not quite.
A does not equal, A equals 0.
Yeah, so you must have A equals 0 and B not equaling 0. Now, I don't know how to make sure that B doesn't equal 0, but I know it's pretty easy to figure out what makes the numerator 0. So set the numerator equal to 0. And so that's 3x squared minus 12, so I can divide both sides by 3 and I get 0 equals x squared minus 4. How do I solve this? Somebody from the south side. Oh, yeah.
You add the left, or the 4 to the left side.
It's a more dependable way. Start with and rhymes with actor.
Factor.
Excellent. So what are my solutions? X equals minus 2 and x equals 2. So those are the ones that make your numerator 0. But we have two conditions here. Yeah.
You have to plug them back into the equation to make sure none of them make b equal 0.
Great. So we're going to check the denominator. So when x equals minus 2, the denominator equals 2 times the square root of minus 2 cubed minus 12 minus 2 plus 16. So that's 2 times the square root of minus 8 plus 24 plus 16. So that's 2 square root of 32. Oh crap, we don't have calculators.
It's not 0.
It's not 0, that's the main thing. So that's definitely a solution. What about when x equals 2? The denominator is 2 times the square root of 2 squared minus 12 times 2 plus 16. That's 2 square root of 0. That's 0. Whoa. It's a good thing we checked. These are easy to find, but you really have to check both conditions. So the only valid solution is x equals minus 2. Now, I want to show you this because it's really cool, as opposed to all the other stuff we do also. we do our original function, which was square root of x cubed minus 12x plus 16. Look at that. So at x equals 0, notice the tangent line has a negative slope. We know the slope was negative 3/2. At x equals negative 2, there's a horizontal tangent line. At x equals plus 2, there's no tangent line. So that's a really cool problem. Repeat after me, yes, this is really cool.
Yes. Very cool.
Very nice. All right, now, we've got just a few more minutes. Example 3. Find the derivative of f of x equals tangent squared of cos x. Well, notice that f of x can actually be written, and ought to be written this way. It's a function inside of a function inside of a function. So when you go to do the tangent, when you go to use the chain rule, what's the outer function going to be? Or actually, all right, so this is like Shrek in the Onions, right? What's the outer function?
Parentheses squared.
Yeah. When you're looking at this thing from the outside, all you see is the outer function. Now, what's the inner function? Somebody else. Your hands up. Your elbows up.
Tangent. Cosine of x.
Yeah, tangent of cos x. All right, so what's outer prime? You're overworked. Your hand is almost up. If this is the outer function, what's outer prime? Good. Now, if this is the inner function, how do you get inner prime? Not the product rule. So to get the derivative of this, it's another chain rule problem. So my inner function is a function with a variable. So what's my inner prime? Minus sine of x. What's my outer function? Well, my outer function is empty. It's tangent of the parentheses. Now, anybody remember what the derivative of tangent is? Good. So outer prime is secant of parentheses, that whole thing squared. So when I assemble this, these chain rule details, this is all just to get the inner prime. I have to get secant of parentheses squared. I've got to put in the original inner function, cosine of x, and then I have to multiply by my inner prime, which is parentheses minus sine of x. This is a monster problem. I love it. So f prime of x is, I got to go get my great big outer function, 2 times parentheses. And I plug in my original inner function, tangent of cos x. And then I have to multiply by my inner prime, which is this mess. Secant of cos x, that's all in parentheses squared, and then this is being multiplied by minus sine of x. Isn't that cool?
Yeah, cool.
That's it. So that's one twist. You can have problems where you have to use the chain rule more than once. In your homework, you're going to find some other twists. Like there's some problems where you have to use the chain rule and the product rule. And it's just going to be, when you're confronted with a function, just depending on how it's built, you have to use the appropriate rule. Sorry to keep you late. I'll see you on Friday.